let us use some examples to deepen our understanding of this shattering definition, right? We're looking over a set of infinite hypothesis spaces and see how many points can they shatter, right? So the example one is called left bounded intervals. So each classifier is represented by a left bounded interval. So the left end is 0, fixed, right? Right end is A. So A is kind of a free parameter which must be positive. So all the examples inside this left bounded interval are classified as positive, outside classified as negative, right? So obviously, the left bounded intervals can shatter 1 point, right? So if you have some point, right? See here, if it is when you give the label as positive, you can make A on the right, right? It gives the correct prediction. If it is if the label is negative, you can put A on the left hand side, so you can give correct prediction, right? But is it able to shatter 2 points? Yeah, I saw someone shake their head, right? Say no, right? We can take a look, right? So suppose I'm giving 2 points, right? Remember, shattering means that, okay, for every possible label in this game, they can find an instance which can correctly predict labels, right? So these are my 2 points. Suppose I give the left point a negative label and positive label to the right point, right? You will see that we're never able to find a left bounded interval which can correctly predict both labels. Why? We can do a little bit of analysis, right? If we put A here, right, left to the left point, all the points, both points will be labeled as positive, right? If we put A here, right, right to the right point, both points are labeled predicted as positive, right? If you put in between, well, you're gonna predict the negative point as positive and positive point as negative. So now you can see how weak these left bounded intervals are, right? So although they are infinite hypothesis spaces, they can only shatter 1 point. They cannot shatter 2 points.
I'm having a hard time differentiating between this shattering concept and like attitudes to using like lazy learners. Like, am I just missing something? It seems like because you can use lazy learners to learn functions, like we did in additives.
Oh, right now we're not talking about how to learn that. We're just talking about when you're talking about lazy learners, is talking about how do you search those hypotheses in a hypothesis space. Right? Right now, just assume that okay, you're given this hypothesis space, right? And we're not talking about how to reach out to a specific hypothesis. We're talking about if there exists a hypothesis which can correctly label, correctly predict all the labels. Like you can say even for the existent statement, you cannot satisfy this, right? Because when you label your 2 points in this way, throughout the whole hypothesis space, you won't find any instance which can correctly predict both labels. Okay, so now let us increase the flexibility a little bit more, right? Now my hypothesis space is intervals, free intervals, meaning that okay, both left and right end are free parameters. We only need to satisfy that B bigger than A, right? Otherwise it won't be a valid interval. So we see that, okay, again, I mean, our classifier is defined the same as the left bounded interval. All the points inside the interval are classified as positive, outside negative. Okay? So these points These intervals, free intervals, this hypothesis space are flexible enough to shadow 1 point and 2 points, which I'm not gonna explain, right? I will leave it as an exercise for you, right? But it cannot shadow 3 points. So just random pick up 3 points here, right? And I'm considering a specific labeling scheme where the two ends, right? Left and right end points are labeled as positive, and in the middle, negative, right? So you'll find that you will never be able to find an interval classifier which can correct label all the 3 examples. So you can try that. If you put A here and B here, and the other 2 outside points are labeled as negative, which is wrong, right? If you put A here and B here, the other 2 points, the first one and the second point, are labeled as negative, which are not right? If you put in between, well, you make wrong prediction for all the 3. Right? So I'll leave it as an exercise for you to justify this point. It's actually the free interval hypothesis space is more flexible than left bounding interval space. In that, okay, now they can shatter 2 points, but they cannot shatter 3 points. So you can see that their expressiveness is still quite limited. Right? Now, if we switch to lines, or in other words, subspaces in the plane, we see that it is this is an even more expressive hypothesis space because it can shatter 1 point, it shatter 2 points, it can shatter can it shatter 3 points. This is something we're interested in, right? How can we examine if they can shatter 3 points? Yeah, there's no tricks on that. You just enumerate all possible labeling schemes. And for all possible labeling schemes, you can test if you can find a hypothesis which is a line which can correctly predict all the 3 labels, right? Actually, because you have 3 points, you actually have 8 possible labeling schemes, right? And for every labeling scheme, you can find a corresponding line which perfectly separates positive and negative examples, meaning that they give a correct prediction of all the labels. Then we'll conclude that, okay, linear classifiers on the plane can shadow 3 points. In other words, linear classifiers are even more expressive than free interval space, right? But how about 4 points? Can linear classifiers on the plane shadow 4 points? Yeah, intuition is correct. In our class, in our homework assignment, there is a bonus question asking you to show that. Right? And if you're interested in doing that, well, it's kind of like a little bit tedious, but just follow the definition. You enumerate all possible layouts of the 4 points, and for each layout where you examine the labeling scheme, you'll find that not any layout of 4 points for every possible labeling scheme, you can find a corresponding linear classifier which gives correct prediction. So you can see that shattering is like playing an adversarial game. Right? So you claim that your hypothesis class H can shatter these E points, and adversary says, okay, that's where you think. Look at this labeling scheme, right? Can you win it, right? And you're working out some hypothesis in a hypothesis space, right? And that correctly predicts your evil labeling. And then the adversary will propose another tricky labeling scheme and challenge you and say if you can give the correct prediction by finding a specific function in your hypothesis space. You do this again and again, and finally you can end up with the conclusion if your hypothesis space can shatter these points or not. So if you have a hypothesis space H which can shatter an arbitrary large number of instances in the instance space, then we claim that your hypothesis space can shatter infinite number of points. So this is kind of like a subtle definition. So don't think of like, okay, if someone said, okay, your hypothesis space can shatter infinite number of points, meaning that it can really shatter infinite number of points. It's just saying, okay, you can give arbitrary number of finite points. Your hypothesis space can shatter. And intuitively, the larger the subset of instance space that can be shattered, the more expressive the hypothesis space H is. Any question regarding the definition of shattering? Hopefully those examples can give you a concrete idea about how this is defined and how it reflects the idea of the expressiveness of capacity. Okay, now we can take a look at the definition of the VC dimension, right? As we just mentioned, right? The VC dimension is defined on the concept shattering. So the formal definition is as follows. The VC dimension of a hypothesis space H over instance space X is the size of the largest finite subset of X that can be shattered by H. So two key points here inside this definition, right? That which can be easily confused. People are easily confused here. So if there exists any subset of size D that can be shattered, then we'll claim that the VC dimension of your hypothesis space H is bigger than or equal to D. Right? In one subset. So don't get confused here. If your VC dimension is bigger than or equal to D, as long as you can find one subset of size D which can be shattered, it does not require you to ensure every subset of size D to be shattered. So as long as you can find a subset of size D which can be shattered, then you can claim, you can safely claim, okay, your VC dimension is at least D. It doesn't require you to shatter every subset of size D. So don't get confused here because many people are confused at this point. So secondly, only when no subset of size D can be shattered, the VC dimension is less than D. So it's kind of like a little bit weak condition. As long as you have one subset of size D that can be shattered, then you can claim, okay, my VC dimension is at least D. Right? Only when no subset of size D can be shattered, okay, you can claim, okay, my VC dimension cannot be D, right? Must be less than D. That is why it's defined as, okay, it is the size of largest finite subset X that can be shattered H. This is the VC dimension. So if you want to show that, okay, the VC dimension of your own classifiers is 3, what you need to do is just to show that, okay, you can find 3 points, whatever layouts, they can be shattered by your hypothesis space. At the same time, you need to show that any subset of points of size 4 cannot be shattered by your hypothesis space. Okay, any question regarding the definition of VC dimension? Okay, great. So let's stop here.